Very good morning. Welcome you all to the NPTEL course on electrical distribution system analysis. And today we are going to focus on aspects related to power quality, reliability, and availability in connection with distribution systems. Now, one thing is very clear. Whenever we talk about reliability and availability, the energy or the power availability play a very crucial role with respect to reliability. For an example, there are many factors which may affect reliability, but if you look into this diagram, power outage, which is playing the maximum hampering role related to reliability, which is as high as actually 90% plus. Computer hardware problems, which is close to 50 to 55%. Telecommunication problem, which is close to 50%. Lightning storms may hamper business disruption close to actually 40% approximately. Floods around 20%. Fire around 15%. Hurricanes 15%. Earthquake 10%. As well as violence, bombing, and terrorism up to 5%. Means the business of any country depends on no outages related to energy at any cost, because that is the maximum variable which may affect your country's economy. Now, when we talk about reliability in general, we'll start from what is contingency. Contingency, which is an unexpected event such as a fault of an open circuit. Another term for a contingency is an unscheduled event. But we carry out contingency analysis to make sure that due to failure of any element or equipment of any system will be protected through a replacement scenario. The second one, we talk about open circuit, that is a point in a circuit that interrupts load current without causing fault current to flow. Next is fault. Fault is a short circuit. Faults are caused by dielectric breakdown of insulation system and can be categorized as self-clearing, temporary, and permanent. Outage. An outage occurs when a piece of equipment is de-energized. Outage can be either scheduled or sometimes it is unscheduled. Availability. The possibility of being energized is known as availability, and the possibility of not being energized is known as unavailability. Now, when you talk about availability, that availability percentage could be 90%, 99%, 99.9%, and sometimes it is as high as 99.79, that is close to 100%. So, it has been known as actually 1929 up to 99. So, when you talk about 99s, which is almost it is available to you, and 19 is almost available up to 90% of the year. Now, in the first case, when we say 90%, the annual interruption time is 36.5 days, that is 10% of the year. And when you say 99%, it is 3.7 days of interruption. And if you come down to 99.79, that is total 9 nines, which is of 1.9 cycle of interruption, means almost there is no interruptions. Many manufacturing plants requires 6 nines, that is corresponding to an availability of 99 plus 99.49%. And when you say actually 6 nines means almost 31 seconds in a year, interruption may be there. Internet data centers may demand reliability as high as 9 nines for their servers. less than 2 cycle of interrupted power per year. So almost no failure around the year. Now this a relationship between power quality and reliability. If you look at this diagram, so the whole segment which is represented by power quality, and within which we'll find actually reliability, and within which we can find availability. So to us, availability is a subset of reliability, and reliability is a subset of power quality. Now there are few definitions which are important for all of us to understand before we get into reliability studies. The first one is actually SAFI, System Average Interruption Frequency Index, SAIFI, which is the ratio between total number of customer interruptions upon total number of customer served. Now this is one of the case study with 50,000 customers, where you can see different date and time as well as the customers affected, duration of interruption, and then customer minutes, which are totally approximately 21408 customer minutes being the total interruption, that is the customer times the duration they got affected. If I calculate what is SAIFI SAFI, so that is nothing but the total number of customer interruptions, that is 1014, upon the total number of customers served, which is 50,000. So if you are interested to calculate the variable or the factor SAFI, which is 1014 upon 50,000, and that is 0.02028. We can also calculate one more variable known as SAIDI, System Average Interruption Duration Frequency Index. SAIDI, SAIDI is defined as the ratio between sum of all customer interruption durations upon total number of customer served. With the same example, we will try to calculate what is SAIDI. Now, it says the ratio between sum of all customer interruption durations, that is customer multiplied by the duration, that is 21,408 upon 50,000, which is 0.428148. So this is how for a given case study one can calculate what is SAIDI, that is SAIDI. We can also define one more variable, which is KD, CAIDI, Customer Average Interruption Duration Frequency Index. KD is the ratio between SAIDI upon SAIFI, that is sum of all customer interruption durations upon total number of customer interruptions. For the same case study, if you are interested to know what is KD, that is sum of all customer interruption durations, that is 21,408 upon the total number of customer interruptions, which is 1014, and the ratio will be 21.11. So based on the same case study, we can calculate SAIDI, SAIFI as well as CAIDI. Now we'll move to Average Service Availability Index, that is ASI, which is the ratio between SAIDI upon SAIFI, customer hour service availability upon customer hours service demanded. If you take the same case study, probably you can calculate which is ASI, which that is customers hours service availability, that is total customer 50,000 multiplied by 8,760 hours, multiplied by customer got interrupted. They are 1014 times 7.38 hours. This will give me the customer hours availability. Am I right? Upon the customer's hour service demanded, because everyone expect the service to be 100%, that is 50,000 multiplied by 8760, and that is 0.9999829 is my ASI. Now we'll move to, there are some less commonly used reliability indices. They are not based on the total number of customers served, but based upon the number of customers that have experienced one or more interruptions. For example, when you talk about CAFI, that is CAIFI, customer average interruption frequency index, that is total number of customer interruptions upon customers experiencing one or more interruptions per year. Similarly, you can define CTAIDI, that is customer total average interruption duration index, which is the summation of customer interruption durations upon customers experiencing one or more interruptions hours per year. The increasing sensitivity of customer loads to brief disturbances has generated a need for indices related to momentary interruptions. MAIFI, that is Momentary Average Interruption Frequency Index, MAIFI, which is total number of customer momentary interruptions upon total number of customers served per year, as well as you can define MAIFIE, that is Momentary Event Average Interruption Frequency Index, that is total number of customer momentary events upon total number of customers served per year. What I wish to highlight here, in a given database for a small case study of a village or an institution or a city, all these variables can be easily identified, and they are the indices that defines how reliable your systems are and how interruptions are frequently occurring in a system. So we'll just go for an example to understand few reliability indices. One breaker operated twice affecting 1015 customers, and 4 other breakers operated once affecting 867, 2005 and 1330 customers. The utility serves 50,000 customers, then what is the MAFI, that is MAIFI. So let us solve this problem. First of all, we need to calculate the total number of customers momentarily facing interruptions. That is, there are twice affecting 1015 customers, that is 2 times 1015 plus 1 times 867 plus 1 time 2005 plus 1 time 1330. So total interruptions are 6232. Now if you need to calculate what is MAFI, that is 6232 upon 50,000, that is 0.1246 will be my MAFI. But if I have to calculate what is MAIFIE, there actually we have to calculate the total number of interruptions, that is total number of customer momentary events upon the total number of customers served. So in that case, we have to simply add 1115 plus 867 plus 2005 plus 1330, that is equal to 5217 upon 50,000, which is 0.1043. So this is how actually you have to calculate different indices of reliability. To fairly weight larger customers, load based indices are available, and they are ASIFI and ASIDI are equivalent to the SAFI and SEDI. Now, if you talk about average system interruption frequency index, that is ASI-5, connected kVA interrupted, because this is related to energy, upon total connected kVA served. Okay. Similarly, if you are interested to calculate what is ASI-DI, average system interruption frequency index, that is ASI-DI, connected kVA interruption duration upon total connected kVA served. Now, if I have to plot for a given case study different usage of reliability indices and percentage of utilities using those indexes, now SADI will be almost quite high, then you see SAFI, then KD, then SI, then MAFI, then SIDI, SIFI, CIFI and CTIDI. So, this is how the indices are expected to behave. Now, we will move to power quality, which is also an important issue within your distribution systems. So, first of all, what is quality of power, and how power quality problem actually arises? The electric utility is supposed to provide the customers with an ideal voltage that is purely sinusoidal waveform with constant magnitude and frequency. So, the voltage signal is expected to have constant voltage and frequency, but which is practically not possible due to presence of many power turning devices and other practical scenarios. Problems generated by the electric utility causing problems at the customer's premises, that is sizing and location of capacitors, transformers, line design and harmonics due to transformer magnetizing current. So, the moment you have transformers within the system, which is a mandatory device, you cannot be completely free from harmonics. Problems generated by a consumer causing problems to another consumer, that is welding machine, rectifiers, furnaces, motors, etc. So, these are the devices when you use, probably you are prone or you are forced to inject harmonics to the distribution system. So, a consumer which is next to a welding machine system will automatically face power quality challenges, though that fellow is not causing any issue to the system. Problem generated by a consumer causing problems to his or her own equipment, that is harmonics, unbalanced loading, poor connection, etc. being the major cause. Now, first of all, try to understand what is interruption. Interruption means, as you could see, this is my pure sinusoidal constant voltage signal, but suddenly you see there is a break. Okay? So, you do not find any signal at all in between, and you feel that there is an interruption in between the signal. And interruptions are of different natures. There are instantaneous, momentary and temporary interruptions. So, when you talk about instantaneous, that means approximately 0.5 to 30 cycles, that is less than 0.1 per unit time, that interruption may occur, and probably in case of momentary interruptions it could be 30 cycles to 3 seconds, and in case of temporary interruptions it is 3 seconds to 1 minute. All right. So, this is the type of interruptions any distribution system may face. We will move to one more interesting power quality topic, which is sag or deep. Now, in case of sag or deep, what we see that instead of a pure sinusoidal constant magnitude frequency signal, you will experience a drop in the maximum magnitude of the voltages or any signal. Okay. So you see that after this point probably there is a drop in magnitude and that continue for reasonably a particular period and then continue to be normal. So this is the area or this is the duration between which we can say that the signal experienced sag, means the magnitude reduced. So sag dip also takes place for 5.5 to 30 cycles, and in case of momentary it is 30 cycle to 3 seconds. In case of temporary it is 3 seconds to 1 minute. Voltage sags are temporary RMS reductions in voltage, typically lasting from a half cycle to several seconds. Sags results from high current, typically due to fault or starting of a motor. They are a major power quality concern since they can cause sensitive electronic equipment to fail. The magnitude of a sag is described by either the resulting per unit voltage or the per unit voltage decrease below its normal value. Similarly, we will move to one more variable known as swell. The name itself speaks that the voltage has increased. So, you could see similar to sag in case of swell, the magnitude, the voltage magnitudes, that is temporary RMS, increases in voltage, typically lasting from a half cycle to several seconds. Swell are commonly caused by the de-energizing of large loads or asymmetrical faults. Swell can cause insulation breakdown in sensitive electronic equipments. Now we'll move to transient. Transient is a very interesting phenomena. I think in this diagram all of you can see this cycle where you could see there is a spike. So we call it as a transient signal instead of a pure signal. Voltage transients are sudden, non-recurring changes in voltage magnitude. Transients are sometimes referred to as voltage surges or voltage spikes. An impulse transient most commonly caused by lightning or switching operations. Oscillatory transient typically caused by capacitor switching and ferroresonance. If you get into the transients, for example, there are impulsive transients which are of 5 nanosecond rise, some of them are microsecond rise and some of them are millisecond rise. Next one is noise. So noise can be broadly defined as unwanted voltage signals with broadband spectral contents. So each and signal you will see there is a spectral content. Common cause include power electronics, control circuits, arcing equipments, loads with solid state rectifiers and switched mode power supplies. Noise problems are often exacerbated by improper grounding, and you could see that the noise which is broadband and steady state which is varies between 0 to 1%. So the signal you can say full of noise, which is quite common in real time distribution systems. The next one is harmonic distortion, where you have the pure signal, and the second one is harmonics. A current waveform distorted by harmonic caused by a various nonlinear devices. This current will cause harmonic voltage distortion as it interacts with system impedances. Voltages with high harmonic distortion can cause a variety of equipment. Problem and recommended harmonic limit are described in both US and European standards. The next one is frequency variation. So the first one I could see that there is a constant frequency happening, but in the second signal you could see the frequency is suddenly varied and then finally become constant. Voltage frequency is directly proportional to the rotational speed of synchronous generators. Frequency variations occur when generators adjust to change in system loading. Large frequency variations are rare in highly interconnected systems. More commonly occurred when isolated generators have control problems, cannot properly track large changes in load or speed up after a system fault. Now we'll move to flicker. Voltage flicker refers to low frequency variations in RMS voltage that cause visible changes in the brightness of incandescent lighting system. These voltage variations are caused by the cycling of large loads such as refrigerators, air conditioners, elevators, arc furnaces, and spot welders. With this, we are coming to an end today. Thank you very much for your patient hearing.